So great, welcome everybody now to the first session in English at the Vintage Computer Festival, and something we delve into programming. We delve not only into programming from the 70s, 80s or 90s, even before to the 60s. And we have here Neil and Lena, which are working for New Voice, and they're gonna show us what they did actually with the Apollo guidance computer and what they programmed for it. So say hello and just welcome them now.
Thank you. Thank you for the introduction. So in July 1969, 3 astronauts went towards the moon. They are Neil Armstrong, I think I might be named after him, Buzz Aldrin, and the other guy. This talk is about the other guy. His name's Michael Collins, and he didn't land on the moon. While his friends went down in the lunar module to land on the moon, Michael Collins stayed behind in the command module to wait for them to come back up. Back then, automation wasn't so great, and so somebody needed to be in the loop to solve problems. And he went all the way to the moon, didn't get to land, but there was another problem with his flight.
Since he had to stay back in his command module with an important job of keeping it alive and making sure that when the lunar crew comes back, that they can safely dock back and return to Earth. His orbit around the moon took 22 hours, and during this, he was the world's loneliest man alive, because when he traveled to the far side of the moon, he was 97 kilometers away from the closest human. He also lost communication with the Earth for about 40 minutes. So he was totally alone in his command module and, well, had actually the state-of-the-art computer back then, but didn't have any games.
So the computer that he had was the Apollo guidance computer. It was a miracle of modern technology for the 1960s. It was the world's first computer that used integrated circuits instead of discrete components. Most people who talk about it say a lot about its memory. It had less than 4 kilobytes of memory, which is not great. But it was actually an extremely powerful computer for even 20 years later. Not counting the memory. It ran at 1 megahertz, which is crazy fast for the 1960s. And it had 15 bits on the of numeric precision. And a lot of the opcodes are designed to use that in double format, so you can get twice as many, 30 bits. And that level of precision is required if you're going to do trajectories to the moon and not miss it. So this thing was, there were 2 of them, one in the lunar module that went down and performed the landing, and one in the command module. So what we decided to do was, 55 years too late, write some games for the Apollo guidance computer. And, well, the first thing to do is to write Hello World.
So we then came up with a program that simply counts up from 0. We have a magical register that is located in the octal number 7, and it is hardwired to 15 bits of zeros. So first step, we clear the accumulator. The accumulator is basically well, the register that most of the functions use for multiplication or addition. We clear the accumulator and add the 0 into it. Then we transfer that to the storage in any erasable memory location, in this case 1, 2, 3, 4. And then we create a loop that we augment the number. The extend is there because they ran out of opcodes. So with an extra extend opcode, they can double the total amount. And augment in this case, it does two things. If you have a positive number, it counts up. But if you have a negative number, it counts down. And you might be wondering, you have 0. What does it do? That's the fun part. You have to pay attention if your 0 is positive or negative. And if you forget to pay attention, you get into trouble.
So if this program worked, we'd be done. We'd have a hello world. Unfortunately, it doesn't work because you put this in and turn on the computer and nothing happens. The computer is hardwired to start executing code at instruction location 4000. So if we prefix this with setlock 4000, then that means that this address the program starts at that location, and so you power it on and it runs. Side note, 4000 actually isn't 4000. Everything's an octal, but we're just going to say 4000. So this will actually run just fine, but then it gets unhappy because 4000 is not the only magic memory address.
Exactly. Not only is 4000 a magic memory address, so is 4004, and so on and so forth. Basically, the AGC is expecting that at 4000, it gets its startup program, and at 4004, it gets its program when time 6 overflows. So this is an interrupt jump table. That means every time that there's an interrupt, is it a key press or the joystick interrupt, it will go to that line and execute it. So in this case, we had to tell it that on startup, it should jump to our start program and then do its function.
And if you don't have a resume function on each of the interrupts, it gets very unhappy very quickly. That was one of the problems that they had on Apollo 11. Now, the next problem, going to the next slide, is that the operating system is designed to be multitasking. Now, our program is not, but the operating system is designed to be checking all sorts of different parameters and running different programs at the same time. And in doing so, it will periodically check a memory address to find out what the next task that it should be running is. And that is so much of an assumption that there's hardware in the computer that checks to make sure that you are looking at address 67, again octal, and if you don't look at address 67 within, say, about a second, then the hardware assumes that your program has crashed and it reboots the computer. So if you are if you're writing things from bare metal, then you need to continuously read address 67. It's conventionally known as new job. And just that act of reading it, you don't have to do anything with it. Then it will pacify the night watchman, which would otherwise reboot the computer. Reboots are really fast, though, but it does reset your data.
Well, not only does it check for if you're reading from the new job location, but it is also checking that if all the interrupts are functioning, or not all, but just some interrupts. So the AGC is expecting to have an interrupt every 140 milliseconds. If this does not happen, then it will restart the computer again. So what we have to do is, on startup, we have to tell it to schedule a T5, time 5, interrupt in 100 milliseconds. And then it can go to do our program. And after 100 milliseconds, the time 5 overflows. And when it overflows, we tell it to do reschedule another interrupt in 100 milliseconds. And this will solve our no-rupt problem. So the computer now does not reboot every 100 milliseconds.
So that's all the steps you have to go through to keep the hardware happy. However, there's a problem with this in that every 100 milliseconds when T5 runs, it clobbers the A register. So if you've been doing anything, then after 100 milliseconds, your data gets corrupted. Now, in any modern, normal computer, what would you do? Push it to the stack, exactly. What do we not have on the AGC? A stack. So, what we do have on the AGC, though, is a dedicated register called A-interrupt, A-rupt. And so, first thing you have to do is move it to interrupt, move it to this dedicated register, do our thing, and then bring back the original value. But you don't do, yeah, you're right. The whole concept around the AGC is it's got single level of function calls, single level of interrupts. If you violate that, you get in trouble really quickly. It would be really nice if we had a stack, but we don't. So yes, store it into ARupt, restore it, and then we're no longer corrupting the program. But maybe you've seen the problem here.
I think you meant that.
The resume is located on the interrupt vector.
Exactly. That was our next problem. So that basically we have to move the last exchange of the ARupt into its new little program or loop, jump place. And since we anyways have a new jump place that we will do every 100 milliseconds, we can also directly put the new job reading in there. So that means our program up there would be its own little program without any distractions.
So that is everything you need to get basically Hello World working on the AGC. A little bit of boilerplate, but then you've got your code in here and you can keep on programming. And it's actually a lot of fun. Once you get past the expectation that you're going to have a stack, it's actually good. So then the next question is, how do we get Doom ported to the AGC? And the short answer is you don't. And the reason is that this is your I/O. You've got a number pad. It's OK. But your display, you can display 3 5-digit numbers as well as a little bit of other extraneous data. And yeah, I don't know how to port Doom to that display. What will work, though, is tic-tac-toe. Tic-tac-toe is perfect for this grid. So now we just need to figure out how do we find an AGC to program on.
And currently there are 2 physical AGCs that are outside of museums. One has been auctioned off to a private collector for $300,000. Well, the original price costed NASA $1.5 million in today's money to build the AGC. So actually, it's a steal. And the other one is free to take. That is, if you can get your hands on it. And if you don't have a spare rocket ship in your backyard, it might be a little tricky because it is currently in the solar orbit. And since we lack the essential resources for both the options, we turn to the virtual AGC. And we're lucky that a group of enthusiasts, they have digitalized all the code of the AGC and created a virtual machine to simulate the AGC that you can run now on a laptop.
Which one is around? The Apollo 13 one?
No, that one burned up in the Earth's atmosphere. It's Apollo 10. They almost landed, but didn't quite.
And then they ejected the...
Yes. Yeah, and it's still out there.
Presumably there are some on the moon.
No, there are none on the moon, because when they take off from the moon, they leave behind the descent module, which is basically dead and inert, and the ascent module comes up with the AGC, but then they crash them back into the moon to produce moonquakes to find out what the internal structure of the moon was. So they served a good purpose.
On the moon, they're just a little...
Some assembly required, yes. True enough. They did make 70 of these. About half of them, probably a little bit less than half of them, ended up in spaceships in one way or another. But the rest just got scrapped. And there's only one that survived, which is, yeah, a real shame.
I'm also not sure if you would want to reassemble an AGC because its memory was hand woven. So you would basically have, I think, 3 months for one of the plates. Let me go back. One of these plates took 3 months to weave every single line of code, basically. A bit.
Yeah. It was a core rope memory, which is fun. So you had women at Raytheon weaving. If the wire went through the ferrite core, it was a 1. If it went around, it was a 0. And yeah, you have to make sure that you've got the right code before you commit to weaving it. So, demo. This is the virtual AGC simulator, and free to download. It's wonderful. In this drop-down list, we can see all the different versions of the flight software. Apollo 10 command module, that's Comanche, that Michael Collins would have been running. And then you've got Luminary, which actually landed on the moon. It's quite an impressive archive here. And at the bottom of this list, we've got tic-tac-toe. So we'll just run that. Who here knows how to play tic-tac-toe? Come on up. Yep, you want to play? Yeah. You're Michael Collins for the day. So that was 13, and it was past tense. We've had a problem. Now, one of the limitations here is that what we've done is programmed it from the bare metal. So if Michael Collins wanted to play this game, he would have had to power down the computer, use a screwdriver to extract the rope memory modules that were provided by NASA, insert his own that he somehow managed to bootleg onto the ship. There were quite a few things bootlegged onto the ship, but let's talk to Apollo 12 about that one. And then power it back on with his new rope memory, and then he could play tic-tac-toe as long as he was behind the moon. And then before he gets reacquisition of signal, he's got to take that out, reinstall it, power up the AGC, align the star trackers, get everything ready so that NASA wouldn't know that he's playing.
You meant that's what we did.
That maybe. Okay, well, we will continue. We'll get this demo working so that you can play with it after the talk. In the meantime, are there any questions?
Why bare metal? Why not use the OS?
So the OS is a whole nother level of complexity. It's designed around the concept of verb-noun interfaces, and we wanted a program where you could just click a button and play somewhere and not have to type verb 66, noun, whatever, enter, and play somewhere. It just gave us much more freedom to access the hardware directly. But yeah, that was certainly a consideration. Yeah. So we had, I believe, around 700 lines of code. Wasn't too bad, but I don't know what that compiles down into. However, the rope memory is, the size of the rope memory available is actually quite extensive. That's not the limiting factor. The limiting factor is the random access memory, which is just under 4 kilobytes, roughly. But those words are long. They're 15-bit words, so you can pack a lot into a byte if you choose to do so. We could certainly have done a lot of optimizations to shrink it down further, and if we were actually going to do that, then we would have, but we didn't need to. I would prefer to have legible code than code that can fit. On site? Okay. Yeah?
I was wondering, have you played with the idea, or maybe are there projects out there to extend the I/O, the interface to the HEC, maybe to get this dream of Doom running on it?
Well, the AGC actually comes with a lot of interesting I/O by default. You've got hand controllers, and not too many computers in the 60s had joysticks. So that was good. You've also got haptic feedback because you could burp the thrusters, which made me think, well, maybe if you lose a game of tic-tac-toe, it burps the thruster, and if you lose too many games, you don't get home. There's some incentive. But yes, the AGC is very, very extendable. It was later used after the Apollo program to fly an airplane, fly-by-wire. That was its last flight. And it was, very easily hackable. There's a lot of I/O pins. There's a full debugger that you can, in hardware, that you can plug onto and see all the registers. It's an absolute dream when it comes to that.
How was the original program operating system debugged?
So they would run it on a PDP-8 to compile it. They had big computers that looked more like this control panel here to run it, and then they crushed it down to something that could actually fit on a spaceship.
So we used an emulator.
Yeah. And there's actually an interpreter on the AGC, which is pretty impressive. At the back there's, yeah. Yep. Sorry, audio capabilities? No. Well, it makes some awesome clicking noises when the display changes. There's some controversy as to whether it could be heard inside the capsule or not. But certainly when you take one of these displays out and play with it, it makes lovely clicking noises. So I suppose you could play William Tell and various other things on it. Yeah. Do we have Leif? Okay.
Turns out it needed Wi-Fi.
It needed Wi-Fi. Okay. Forwards planning there. Right, yes, because there's a connection that uses TCP/IP. Got it. Right, makes sense. Right, would you like to play a game? Why don't you go start? Yeah. Yeah. So we've got 7-segment displays, so we're just going to use zeros and ones. They seem to be the easiest thing. So computer's gone in the corner. And then if you go in the middle, then you've... Well, actually three. Yeah, okay. We designed the software to be a good player, but not a perfect player, because it's really boring to play against a perfect player. The general strategies are, strategy 1, if it can win, it plays in the winning position. If it can block, then it plays in the block position. Otherwise, it plays randomly, which also is a bit of a problem because there's no random number generator on the AGC. Now, if we had a full flight stack, it wouldn't be so bad because we could simply look at the accelerometer, and there's enough bits on that accelerometer that we could get some random data out of it. But as it was, what we did is it simply, in the idle loop, is counting from 8 to 0 over and over again. And on the rare occasions when we need a random number, we just have a look at whatever number is available.
That also explains our Hello World program, why we did a counting loop.
Couldn't you have used the timer interrupt for that and like take some like the lowest few bits of whatever, like by for example not storing the accumulator and trying to intercept?
Yeah, time. We have an idle loop anyway, so we might as well just be using it to count. Yep.
Show some code.
Oh, code. Do we have that here? Yes, we do. Yeah, question? It does not have a character set as such. In fact, it's a real pain to put stuff onto the AGC's DSKY. It's got 5 bits for each tuple, but it's you don't get a lot of flexibility. Basically, it was designed around having the minimum number of solid-state relays in the DSKY. So, no, you've got 0 through 9, you've got a hyphen, and you've got a blank. Those are your supported characters. You've also got a lot of invalid error characters that are just the random result of the circuitry. And unfortunately, none of them are terribly useful for graphics. Unfortunately, no. You do not have pixel level control of the segments, unfortunately. You're pretty much limited to numbers. Yeah. Here's our code. There's our interrupt table. Timer interrupts for keeping the machine happy, as well as blinking. That's once a second. Setting up the game. Here's clearing the board. This looks like really dumb code for clearing the board. Why not use a loop? Well, we did use a loop. It takes 2 more instructions. So unroll it for the win. It's faster, too. And then just a whole bunch more logic.
Is that one instruction per cycle?
I believe so, yeah. And some instructions take two instructions because of extend. They ran out of opcodes, as Lena said earlier, and they used their very last opcode, extend, to double the following.
It's like RISC. Every instruction is the opcode plus of around 50 bits. Take a single number.
It is a little bit more complicated because the opcodes get merged in with some data. That gets deep, yeah. And a lot of these opcodes are aliases for other opcodes behind the scenes. There's a data block down at the bottom that shows the logic of, here we go, values to check. Down a little bit more, it's this data block. So we will check position 7, 8, and 9 because that's a row. And each of the 8 different rows in tic-tac-toe are described by these 3 data sets. Yep.
So your logic for that layer, is it more like heuristics that we implemented, or is it more like a table-driven?
No, it's, there are 3 rules. Play to win if you can immediately. Play to block if you can, and otherwise play randomly. And
Is it like a long sequence of case and if statements?
oh, nope. Lots of loops going over this data structure, looking at different parameters. What we'll do is we will add up the values on the board, and if it's a 6, then that means that it's fully populated. If it's a 5, that means there must be a hole somewhere, and so on. So yeah, we're pretty smart about that. Yep. Yeah, last question?
But you want to present something more?
Nope. That's good.
Any last question?
I think they're not too interested in the AGC anymore, NASA. But I did actually look up to see where Michael Collins is. Unfortunately, he died a few years ago. I then checked all the other command module pilots who were left alone, and unfortunately they're all dead. So we're a bit late.
Okay. Yeah.
Thank you very much.
Yeah, thanks a lot, and an applause for Lena and Neil. Great.